Welcome to my presentation about cross-layer attacks and how to use them for DNS cache poisoning, device tracking, and more. I am Amit Klein from Bar-Ilan University, and this research is part of my PhD thesis supervised by Professor Benny Pincus. Cross-layer attacks use one network layer, such as IPv6, to attack another network layer, such as UDP. We demonstrate these attacks on the Linux kernel, which is used by Linux servers, Linux desktops, Linux laptops, and by Android devices. Prandom U32 is a Linux kernel pseudorandom number generator which is used in over 100 files of the Linux kernel. We focus on the use of Prandom U32 to populate network protocol header fields such as the TCP/IPv4 IP-ID field, the TCP/IPv6 flow label field, and the UDP source port field which is used in both IPv4 and IPv6. Prandom U32 is a Tau-Swather generator with a state of 4 32-bit words, altogether 128 bits. In a PRNG step, a linear matrix is applied to the existing state vector to form the new state vector. This matrix has a rank of 113, so the state is effectively 113 bits. The matrix is fixed, known, and it operates on the state vector on a word-by-word basis, so each word is actually advanced independently of the other words. The output of Prandom U32 is obtained by applying exclusive OR to the 4 words of the state vector. Each Prandom U32 bit is a linear combination of the state vector bits, thus providing one linear equation on the state vector. Using linear equation solving, with enough Prandom U32 bits, the attacker can reconstruct the entire state vector. Prandom U32 has an instance or state per logical CPU core. When a kernel thread invokes Prandom U32, the code uses the instance that belongs to the core on which it currently runs. The initial seeding has all 4 words populated with random data, but reseeding, which takes place every 40 to 80 seconds, overrides only the first state word, nominally 32 bits and effectively 31 states of bits. The implementation is thread-safe but not interrupt-safe. In a cross-layer attack, the attacker extracts the Prandom U32 state from one layer and predicts or matches the next values of Prandom U32 that are used by another layer. Our first use case is effective DNS cache poisoning attack. In a straightforward brute force attack, the attacker tries all combinations of over 28,000 UDP source ports with 64K DNS transaction IDs, a total of almost 2 billion packets. With our attack, the attacker extracts the Prandom U32 state from the TCP/IPv6 flow label field at layer 3, and with this state, the attacker can predict the next UDP source port at layer 4, used for the DNS query, so the attacker has to go over only 64K DNS transaction IDs, a total of only 64K packets. This amounts to a huge saving in both attack time and packets used. In real-life experiment, we demonstrated average time to poison of less than 30 seconds instead of almost 2 days with a brute force attack. Our second use case is device tracking, in which the attacker extracts the Prandom U32 state from a network protocol field and matches it to a recorded state from a previous visit of the device. In this way, the attacker can track devices across IPv4 and IPv6 networks and across TCP and UDP connections. Let's take a closer look at efficient DNS cache poisoning. The attack target is a Linux server, for example, one that runs SMTP service over TCP/IPv6 and uses public DNS services such as Google Public DNS, Cloudflare, IBM Quad9, etc. We ran an auxiliary experiment with Alexa's top 1 million domains and found that between 24% and 37% of enterprise-managed SMTP servers use public DNS service. So this is a very realistic scenario. The attack's goal is to poison the server's tab resolver DNS cache. The impact is extensive. Hijacking emails, this is an SMTP server after all, hijacking HTTP traffic if such traffic is emitted by the machine, poisoning HTTP proxy cache if the target machine doubles as an HTTP proxy cache, and poisoning DNS records which are used for anti-spam and anti-malware services like DNS blacklisting, sender policy framework, and so forth. NTP relies on DNS, so the target's clock can be manipulated, and ironically, strict transport security, or STS, bootstraps using DNS, so it can be suppressed. The attack starts with the attacker probing the target machine over TCP/IPv6, collecting flow label values and extracting the prandom U32 state. Then the attacker starts another SMTP session that triggers a DNS query. This can be done using DKIM, for example. The target stub resolver starts the DNS resolution process by sending a DNS query to the recursive resolver, and that opens the attack window for the attacker, who sends spoofed DNS answers as if coming from the recursive resolver, using the extracted state to replicate the UDP source port used in the original query. The recursive resolver resolves the DNS query and sends the genuine answer to the target machine, at which time the attack becomes ineffective, and because the stub resolver uses the first because the stub resolver uses the first answer that matches the query and drops subsequent queries, so the attacker can halt the attack. And that concludes a single attack attempt cycle. One challenge of this technique is a race condition. The attacker's spoofed response must arrive to the target before the recursive resolver's genuine answer. Ubuntu, which is the most popular Linux distribution, uses by default a stub resolver called systemd-resolved that employs a record-based caching policy. This policy makes the attack much more effective because the attacker can trigger a DNS query to the attacker's domain. In this example, it's dummy123.attacker.site. This may sound a bit counterintuitive. I'll explain why it works in a moment. The attacker's authoritative name server delays the answer. This extends the attack window for the attacker. Finally, the attacker's spoofed answer contains a CNAME chain that ends with a poisonous DNS record mapping an arbitrary hostname www.target.site in our example to an arbitrary address 6666 in our example. Since systemd-resolved caches by record, it caches this poisonous record on its own, overriding any previously cached record if such exists, and serves it for any subsequent query for this hostname www.target.site in this example. Thus, the attacker achieves cache poisoning of arbitrary hostname with arbitrary data per the attacker's choice. Another challenge is accurately predicting the UDP source port when the target machine is multi-core. I remind you that if the DNS query is sent from a different core from the one that the attacker probed, the attack fails. So in order to improve the attack's odds, the attacker sandwiches the DNS query with a post-DNS probe. If the flow label from the post-DNS probe matches the sequence of flow labels predicted from the state the attacker extracted, the attacker can assume that the DNS query was emitted from the same core as well, and the attacker may proceed to attack the target. Otherwise, the attacker can skip this attack and thus save a lot of time and packets. We tested this attack on a machine with 4 logical cores that runs Ubuntu Linux with systemd-resolved stub resolver and Exim SMTP server software. We configured it to use 2 DNS servers, and the attack took place from over 3,000 kilometers away with a modest bandwidth and a very typical RTT. So this experiment represents a very realistic scenario. We obtain an average time to poison of a bit less than 29 seconds versus almost 2 days with a brute force attack. Our attack is therefore 5,000 times faster than a brute force attack. Our second use case is remote device tracking. The idea here is to be able to track a device across websites and across time without using common infrastructure, because common infrastructure is easily detected and blocked. The concept is that each site embeds an HTML snippet with JavaScript. This JavaScript sends multiple TCP or UDP packets to a first-party tracking server, so each site runs its own tracking server. WebRTC can be used to send such packets. The attack can use all combinations of TCP and UDP over IPv4 and IPv6. In our experiments, we used IPv4 UDP source port. The tracking server extracts states from as many cores as possible, and then the tracking server can roll these states backwards to match earlier measurements collected from the same device when it visited one of those sites. The attacker can use the baby steps, giant steps technique to reduce the processing time. The extracted state is not site-specific, rather it is device-specific, or more accurately, kernel-specific, so the attack works across browsers, across containers, and across network switching, including some VPNs, and of course, OS sleep. It does not, however, survive a reboot. One challenge of this attack is reseeding. However, recall that reseeding is only applied to the first 32-bit word, and each word is advanced separately. Therefore, the remaining 3 words are untouched, so there are 82 state bits there that are not affected by reseeding. Another challenge is obtaining p-random U32 bits from UDP source port's observations. The p-random U32 bits are not simply copied into the UDP source port. Instead, the formula in this page is used. However, if we only look at the most significant, say, 8 bits of p-random U32, then these bits are determined fairly accurately by the port value. Therefore, the attacker can still collect enough port values to get p-random U32 bits and extract the state. The third challenge is the issue of drift, wherein the PRNG state occasionally being updated simultaneously when a kernel thread runs and then an interrupt occurs. In such case, since the state cannot be updated atomically, the result is that the first 2 words and the last 2 words get a bit out of sync. This needs to be taken into consideration when the attacker applies the baby step, giant step technique. We tested Android devices from Google, HTC, Huawei, OnePlus, Pocophone, and Samsung, as well as a Linux Dell laptop running Ubuntu. In the Linux Dell laptop, we demonstrated cross-browser tracking between Google Chrome and Mozilla Firefox. We also demonstrated cross-layer tracking with UDP source port, which is layer 4, versus a IPv4 ID, which is layer 3. The workarounds for DNS cache poisoning include using DNSSEC, DNS over TLS, DNS over HTTPS, and TC. But all these technologies are not widely enough deployed. Using OX 20-bit encoding queries is not effective when the target is a record-based resolver like systemd resolved, because the query arrives at the attacker's authoritative name server. And then, of course, it's possible to switch to a stub resolver that randomizes its UDP source ports instead of delegating their selection to the operating system. The workaround for device tracking is using a shared forward proxy HTTP proxy server, or Tor. But the real solution, of course, is to change p-random U32's implementation into a stronger one, which is exactly what the Linux kernel team did for Linux kernel version 5.10 and backported it to all the long-term support branches. To conclude, using weak crypto for network protocol header fields is a bad idea. Industrial strength crypto should be used instead. Using the same PRNG instance for multiple consumers is not recommended. Having a PRNG instance per consumer is better, especially with respect to containers. Partial-only reseeding is potentially insecure. The secure procedure is full reseeding. And an interesting outcome of this research is that the PRNG state itself can be used for device tracking, so sometimes a simple counter is better than weak crypto. Thank you.